Hey guys, it's Mr. Ray here. We're going to start our lessons in the logarithmic functions units. We're going to start off with kind of an introductory lesson on something that you learned in grade 11. That's the exponential functions. And the reason why we're going to introduce or review exponential functions is because the inverse of the exponential function is the logarithmic function. So we don't actually mention logarithmic functions in this lesson, but I guess I'll ruin the surprise for you. Like I just said, the inverse is the logarithmic function. So you can see where, I want you to see where the logarithmic function comes from and how it is the inverse of the exponential function. So hopefully most of this is a review, except for the inverse part. So an exponential function basically takes the form y equals b to the power x, where b is a constant. It's a base. So with the exponential function, the variable is the exponent. So instead of like x squared or x cubed, where the variable is the base, we flipped it around so that the base is constant, but the exponent is changing with the value x, with the variable x. A couple of restrictions on the base. The base has to be positive, and it can't be equal to 1. The reason why it can't equal 1 is because if you had a base of 1, 1 to any power is going to be 1. So if you graphed it, it would just be a straight line, y equals 1. So that's obviously not exponential, that's linear. So we remove the base of 1. We also remove negative bases because if you have a negative base, the value of y will be flip-flopping between positive and negative. And obviously that won't be a function. So it's positive values for the base, except for 1. Okay. Now, another characteristic of exponential functions is if you did a table of values, you will have a ratio. So if you looked at the ratio of one y value compared to its previous y value in the table, it will be a constant. So it's not first and second differences, it's the ratio. Okay, we'll see that in an example. If the value of the base is bigger than 1, well, actually the graph is going to look like this. It's going to be an increasing function. We call this a growth function. So basically the multiplier, the base, the thing you're multiplying over and over by is bigger than 1, so obviously the value of y will grow as well. If the value of the base is between 0 and 1, not including them, 0 and 1, but if it's say 0.5 or something like that, you're constantly multiplying over and over by that fraction or that decimal, so it's actually decreasing by that ratio, okay, or by that factor. So we have a growth function that grows when b is bigger than 1. And we also call this a decay function. So a decay function is when the base is between 0 and 1. Okay, some other characteristics. The domain of any exponential function is all values of x, the real numbers. The range, well, maybe what I can do is start off, you'll have a horizontal asymptote at y equals 0, which means your graph will approach y equals 0 from one side, but never quite reach it. So once you know that, you can say, well, the range is always going to be all real numbers, but it has to be greater than 0. It doesn't include 0 because it never gets there, but everything above 0 it could reach eventually. Okay, and that's true of both the growth and the decay functions. Okay, they both also have a y-intercept of 1. If you think of the function, it would be so base to the power 0. It doesn't matter what the base is. Anything to the power 0 is 1, whether that base is bigger than 1 between 0 and 1 doesn't make a difference. So always y-intercept of 1. Obviously, it's not going to have any x-intercepts because it never crosses the x-axis. Okay, and that covers those. So if we looked at the inverse, so this is the exponential function here. If we looked at the inverse, okay, if you remember inverse functions, you're basically flipping the x and y values in terms of the equation. Also, if you were looking at the graph, it would be a reflection in the line y equals x. So we'll see that in a second. So the domain and the range basically switch, just like I said for x and y. So if you remember, the domain of exponential functions was all real numbers, and the range was y, all real numbers, y is greater than 0. Here it flips. So the domain is restricted for the inverse function. So x is all real numbers, x is greater than 0. And now the range is all real numbers. Okay, so we basically, if you just changed x to y here and y to x, that would be exactly what exponential is. So the inverse, it just flips the domain and range. Now, x-intercept, remember we said there's, with the exponential function, there was no x-intercept, but there's a y-intercept of 1. Well, when we flip it, it becomes an x-intercept of 1. Just change the variables. We had a horizontal asymptote at y equals 0. It changes to, the asymptote changes to x equals 0, which means it's now a vertical asymptote. Okay, and like I said before, the inverse function will be reflected across the line y equals x. So if you remember, y equals x is basically, no, it's that line right there. So if that's the exponential function, the inverse function would be here, and that matches up. There's the vertical asymptote, x-intercept of 1, compared to y-intercept of 1, and a horizontal asymptote at y equals 0. So this would be for the growth function. If you had a decay function, like this one here, the inverse function would look like this. Okay, still has a x-intercept of 1, still has a vertical asymptote at x equals 0, and still has a range y is greater than 0. So everything still applies, but the graphs look a little different, whether it's growth or decay inverse. Okay, so that introduction into the inverse and a review of exponential. Just a couple of quick little questions here, just to get your brain going. So if you had a table of values, okay, and we want to come up with an equation, well, if you looked at the first and second differences, you'd see there's nothing that matches, even third, fourth differences. But you can see that the pattern here is everything's getting multiplied by 4. So if you looked at the ratio of y2 over y1 as your check in this column here, so got 1, 2, and 3. Okay, so the ratio of the y value, so the first ratio would be 4 over 1, 4 divided by 1, so the ratio is 4. Next ratio will be 16 over 4, and that works out to 4, and 64 over 16, that's a ratio of 4. So what this tells you is that you have a ratio equal to 4, and therefore it's an exponential equation. Exponential, let's say function, with the base equal to 4. So the base will be whatever that constant ratio is. So the equation should be y equals 4 to the power x. Okay, and you can easily check this. We can just plug in. So 4 to the power 0 is 1, so that matches up here. 4 to the power 1 equals 4. 4 squared is 16, and you can see the rest fill in pretty easily. So that equation does match that data. Okay, all right. Now, we basically, this equation that we just came up with, we want to look at some features of this function. So this time we're switching from y equals to f of x, so it's in function notation. So we want to look at the domain, the range, intercepts, and intervals for which it's positive or negative. So I'm going to do that. Now, it also says sketch a graph. So I think the graph is actually pretty important to coming up with some of those characteristics or features. So if I was to graph that, we've already got our table of values from up here. So you can see, well, I've got a value f of 0 is 1. And if we went to the left, you'd see it'd be 1/4, 1/16, and so on. So approaching the x-axis very quickly. Okay, so the next value would be x equal 1, y equals 4. So let's say it's right there. And then the next one would be at 2, it'd be 16. So it's way off the graph already. So from here I can see it's going up exponentially, hence the name. And it comes down here and does a screeching halt to when it comes towards the x-axis. So this is your function f of x. Okay, so now let's go back and answer the question. So it wants the domain. So we already kind of learned the domain on the previous page, but let's just check the graph. So we can see either from the graph or the table of values, we could put in any value of x, and we're going to get a valid value for f of x. So domain is x is all real numbers. The range, so y is all real numbers, but y is greater than 0. Okay, x-intercept, well, we know from exponential functions that it doesn't cross the x-axis, so it's none or not applicable. Y-intercept, okay, that's where x equals 0, so if you can tell from here, you just plug in 0 for x, you get 4 to the power 0, which is 1. So the y-intercept is 1, y equals 1. Now, these things here, it wants to know the interval for which the function is positive and intervals for which it is negative. Well, so positive and negative means are the y values positive or negative? So you can see from here that all the values of x produce a positive value for f of x. So we can say that the function is positive for all values of x. So for x element of real numbers. If I was to write negative, it would be the null set, nothing. Okay, so I'm just going to leave it. This lets you know that all values of x are positive, so none of the values of x will be negative or 0. Now, in terms of increasing or decreasing, you can see as we go left to right, the function's always increasing, and that's because it's a growth function. So we can say increasing for all x real numbers, and that covers that. So then the graph, which we did before. Now in the same graph, we want to do the inverse. So this is actually the log function. So remember, it just flips the x and y values, and it's reflected in y equals x, which is my dotted line here. So we know a couple important things. We know it's going to have, instead of having a y-intercept of 1, it has an x-intercept of 1. And instead of having an horizontal asymptote along the x-axis, it has a vertical asymptote here. Okay, so just by kind of coming up with some points here, you can see that the graph will go off like this and then head towards the asymptote. So this would be called, if you remember the notation from grade 11, f inverse of x. Okay, and you can see that it's mirror reflection. Okay, So the purpose of this lesson was just to introduce the concept of the inverse of the exponential function, some of its characteristics, what it looks like on the graph, and basically just to get to know that there is such a thing as an inverse of an exponential function. And in the next lesson, we'll officially introduce it as the logarithmic function. Okay, so there's some homework questions at the bottom here. Just try some of them out. Make sure you're able to do all of them. And we'll carry on with the next lesson, which is logarithmic functions. Okay, have a great day.